Hey, what's up, guys? This is Chung here again. So, this question, number 1739, building boxes. This one is, I think, it's a very interesting math problem. So you have a cubic storeroom where the width, length, and height of the room are all equal to n units, and you're asked to place n boxes in this room where each box is a cube of unit side has one unit as a side length. And there are some rules, right, to place these boxes. And so first one, you can place the boxes anywhere on the floor. That's the given. And the second one is the most important one. Basically, if you want to place any boxes on top of another one, so let's say if you want to place box X and on top of Y, then each side of the four vertices sides of the box Y, which is the one on the bottom, must either be adjacent to another box or to a wall. And then it asks you to return the minimum possible number of boxes, that you need to place on the floor, given integer n. So what does this mean, right? So let's say we have n is equal to 3, right? And then for n is equal to 3, we can only place 3 boxes on the floor. And that's why the answer is 3. But when n is 4, after placing 3 boxes on the floor, and then for the fourth one, we can place that one on top of this on top of this one. Right? So the reason being is that, so for this box, right, all the four vertical vertices, there are basically this boxes has all four neighbors because on this side there's a box, this side there's a box, on the other two side they're like the walls. That's why we can place the a box on top of this one, but we cannot place the boxes on top of this one. Right? The reason being is that, on this side and this side, there's no adjacent boxes, right? So that's that. And yeah, here's like more clear examples here. Now we can place boxes on here, 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 and here because all those boxes on top of this one they all having four neighbors, right? Or either neighbors or the uh, the walls. And then the constraints of n is 10 to the power of 9. So I think to solve this problem, the first thing we can come up is that, let's consider like the complete you can call it a pyramid, right? What is the what is the what does these boxes look like if we can come form a perfect pyramid? So uh, on the first level, right, we can only always place one here, right? That's going to be the one. And then how about on the second level? So the second level is 1 plus 2. And the third level, what is the third level? Third level is 1 plus 2 plus 3. So on and so forth, right? And the fourth level, of course, is 1 plus 2 plus 3 plus 4, and so on and so forth. And that's going to be the total cubics we can place, right? Let's say that the last one is n, right? Plus 3 into n. That's going to be the total number of cubics we can place on a complete n size. N size where n is the longest. You can say the longest diameter, right? Diameter of this cubics of this pyramid. So in this case, it's 3, right? And then so here we have n here. And if we know, right? So if we know the n here, right, and then it's easy for us to calculate the total area of that. And so our strategy is what? Our strategy will basically will try to subtract. So we'll try to subtract the values from this n. The value of what? The value of the of the level of each level of the complete pyramid. So which means that we're trying to subtract one from n, and then from two from n, from the third level, fourth level until the level that we cannot subtract, right? And then we know that the at least we need to have that diameter as the as the last level, right? But on top of that, we still need to consider some of the we might need to, let's say we know that we need at least this kind of size of the pyramid to place the n here, and then for the remaining n's, right? Then we know that okay, we may need to place some more uh, boxes on the floor so that we can place the remaining n's on top of that, right? So basically our algorithm is going to be we try to subtract the from n by using this kind of formula layer by layer we have a until the remaining n cannot be subtracted by the current layer. Then we know that okay, that's gonna be our last uh, level that we need to be considered. But for that thing, but how many how many units or boxes we need to put on the last on the last level here? That's gonna be our another. Let's try to use another example. Okay. Mm. So let's see. Okay. Yeah. So let's say, for example, right, we know that okay. So in this case, we know that okay, we need at least level of level mm, of the perfect pyramid, right? And the remaining n is something like there are like some remaining n's, right? Then which means that we have to add some boxes on the floor so that we can place the remaining n's on this pyramid. But how can we do it, right? So let's say let's try to place the first one here. For example, if we try to place the first boxes here, okay, that's going to be the n, we're going to be n minus 1, right? Because we have placed that. And by placing the first one, can we place more? No. Can we place a boxes here? No, because we cannot place anything on top of the current layer. That's why, for the for the first boxes placed on the floor, we can only subtract one. Then let's try to place another one on the floor, which is the one here, right? So we have another boxes here, right? So let's say this is the first one, right? And this is the second one. So after placing the second boxes here, see what see we can place another one here because this box, right? This box here s satisfy the condition, right? Now meets our condition that all the four vertices have a neighbor. That's why we can place another one on top of this one. So, okay, so which means that for the box for the box two here, right? For the second uh, boxes we place on the floor, we can do we can subtract two here. So let's try to place the third one, right? The third one we place it here. Okay, that's the third box we place on the floor. And then similarly, right, we can place another boxes here. So this is 3. But since we have 2 and 3, and then we can also place another one here. So this is going to be also the third one. So we can subtract 3 here. Similarly for the fourth one, right? So I mean I can draw it here. I mean, so for the fourth one, right? We can place another one here. Uh, another one here, right? That's going to be the fourth one. Yeah, and then another one here, right? Another one here is the fourth one, and another one here. Right, so here I might, okay, on top. So this is the last one, right? Then we can do a -4. So and that's how we calculate how many more like boxes we want to place on the last level here, right? So that we can make n uh, become to 0. And that's how we calculate the final result. Cool. So I think we can try to start coding here. All right, so then we need like 2 answers, right? So first one, I'm going to have a current to help me record our current boxes we have placed so far, and then we have like answer 1 equals and answer 2, they're all equal to 0, which means that our 2 stage of the boxes we place on the floor. So in the stage 1, right? Basically, we're trying to subtract from the or we're trying to add, right, to the current one layer by layer. So on each layer, so how many items, how many boxes on each layer, right? So that's going to be a 1 plus 2 plus 3 plus until n, right? So it's going to be a n times n plus 1 divided by 2. That's the that's the total boxes on each layer, given the n as the as a diameter, right, of this thing. So and so basically, if the current one plus the answer 1 plus 1 times the answer 1 plus 2 divided by 2 is either equal smaller than n. So I do this answer plus 1 and answer plus 2 is because the we initialize answer 1 as 0. That's why on the first level, we should have 1 times 2 divided by 2, which is 1, which is the 1 box. And then we have answer 1 plus 1, and then we do a current plus this, right? Or let's do this, okay? And then we do this one, answer answer 1 plus 1, okay? So and after the first while loop, right? We know that we need to place at least this many uh, boxes on the floor to at least to make this kind of a complete pyramid, so that actually later on, what we're trying to return is that we return answer 1 times answer 1 plus 1 divided by 2, and then we plus the answer 2. Because this answer 1 is only the diameter, and only the length, right, of this diagonal line here. And so that the total boxes with this like answer 1 as the diagonal line here, length here, is this by using this formula, and the answer 2 is the is like what we have here, right? It's the basically how many more boxes we need to put on the floor so that we can uh, accommodate the remaining ends. And so to do that, right, basically our current one is either still smaller than n, right? We do answer 2 plus 1, right? And then we do a current plus answer 2. Yeah. And we do this until we have uh, placed odd n boxes. And that's the remaining boxes we will put on the floor, right? Yep, that's it. Run the code. Mm. Oh, okay. Yep. So that's it, right? I mean, and actually for the time complexity, this is a little bit kind of tricky. The real time complexity is all relies based on this while loop here, right? That's gonna be our biggest time complexity. Actually, the time complexity is how it's to what? It's the n. Uh, actually, it's kind of close to the cubic root of n. And so the reason being is that you know the total number of this complete pyramid is what is actually there's a formula. It's n plus 1. There's n times n plus 1 times n plus 2 divided by 6. That's the formula of the complete pyramid here. And as you guys can see, that's going to be the n, n cube, right? So that since the total one is n cube, and when we are trying to finish the while loop layer by layer, and the time complexity will be uh, the cube cubic root of n, and and how does this formula come from? I'm not going to explain it here. It's more like tool of a mathy problem. So if anyone kind of who is interested, you can look it up online. So there should be some articles online can give you a detailed explanation of that. I'm just using this one as a fact to help me get the time complexity. And yep, I think that's pretty much it is. The code is it's very short, but the idea behind this one is kind of interesting. Especially for the second part, actually. I think for the first one, it's not that hard to come up with, but for the second one, right? The first part is kind of straightforward. Actually, we just need to subtract the cubes layer by layer, right? And but the second part is a tricky part, right? Because for each of the new cube we add on the floor, the more we add it, actually, the more we can stack on top of those. That's how we get this kind of formula to calculate the remaining cubes on the floor. And Yeah, I think that's it for this problem. And thank you for watching the video, guys, and stay tuned. See you guys soon. Bye bye.